Well, welcome back, everybody. And hey, we made it all the way to Chapter 4. Here we go. So in Chapter 4, we study polynomial and rational functions. Of course, we're going to have to learn what that actually means. So Section 4.1, let's learn what a polynomial is. So in this section, we're going to learn how to identify what a polynomial is and something called its degree. We're also going to graph some polynomial functions using these transformations, the horizontal shifts and all that stuff. And then we'll also learn how to identify roots or real zeros of a polynomial and what is called the multiplicity of those things. So first thing first, what's a polynomial? All right, this looks like a very complicated expression, but it's not really. So a polynomial is a function. So here we have a function, f of x. Now here's what we have. We have these a's with subscripts are constants, meaning they're just real numbers. So I have a real number. Let me switch over to the laser pointer so I can point at stuff without necessarily drawing. So what we have is a real number times x to a power plus a real number times x to a power plus dot, 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 a real number times x plus a real number. Now, so all we're doing is we're taking powers of x, multiplying them by things. That's our number times power of x. So I have a bunch of these numbers times powers of x, and then I add up all of those individual terms. Okay, and more specifically, what powers of x do we have? This is an x to the first power. The next will be x to the second, all the way up to x to the n. So the powers of x that we get are actually pretty specific. Okay, so this is a sum of number times x to a power, where the power can be 0, 1, 2, and so forth, up to this maximum power of n. Okay, and that will vary from polynomial to polynomial. Sometimes the maximum power is 3, sometimes it's 12, but it doesn't go on forever. There is a maximum. Okay, and then in terms of some other definitions, n, which is the biggest power, is called the degree, and the a sub n, the number in front of it, is called the leading coefficient. The domain of any polynomial is all real numbers, and let's just see why this is. So look back up here at the real number times x to the power. There could be a problem raising a real number to a power if that power is negative, okay? Because then, for example, x to the minus 1 really means 1 over x, and then I wouldn't want to plug in 0. And if the power was not even a whole number, for example, x to the 1/2, that would be the square root of x, and then I couldn't plug in any negative numbers. But the powers we're using are just these positive whole numbers, squaring, cubing, to the fourth, and so forth like that. There's no issue there, and then multiplying by a real number, there's no issue there, and then adding those things up, there's no issue. So the domain is always going to be all real numbers. Okay. So here's an example. We're going to look at a bunch of functions, and we have to determine if they're a polynomial. If they are, state what the degree is, okay? And if they're not, say what it isn't. Okay, standard form is to go from biggest terms to the smallest, biggest powers of x to the smallest powers of x, and then we should identify what is the leading term and what is the constant term. Constant term, sorry, I didn't define on the previous slide because it wasn't actually given. Good job, book. The number that you have not times x just by itself is called the constant term. Okay, this wasn't defined on this slide, but then in the next one they ask us to use it. So let's take a look. Is this a polynomial? So the first question you ask is, the x's that occur, or the variable if it's not x, whatever it is, but in this case it is x, does every x occur just raised to positive whole number powers? And the answer is yes. I have x to the third power, I have x to the second power, and that's it. And then I multiply by numbers and I add and subtract, that's fine. So this is a polynomial. Okay. The degree is the biggest power of x, which is 3. So it's of degree 3. It's already in standard form because I have the third power, then I have lower powers as I go down until I get down to a constant term. Okay, so they're already listed in decreasing powers. The third power is first, the second power is next. There are no x to the firsts, and then sometimes the constant term is considered to be x to the 0, but that's totally optional. Okay, so the leading term is the biggest power of x. The constant term is the number that has no x's in front of it. I would also add that the leading coefficient is the number multiplying the leading term, and that's 4. Okay, so let's take a look at this example. So again, ask the same questions. Is it a polynomial? If so, what is its degree? Write it in standard form. What's the leading term? What's the constant term? If it's not a polynomial, explain why. So take a moment and do that. So it is a polynomial. The biggest power of x is x to the 4th, which occurs right here. Then I have an x to the 1st and a constant term, and that's it. And then I add and subtract, that's fine. The biggest power of x is 4, that's the degree. If I put it in standard order, I put the biggest power of x first, and notice it's got a -5 in front of it, and then I work my way down. The next power of x I see is x to the 1st, and then a constant term. So the leading term is -5x to the 4th, and therefore the leading coefficient is -5. And the constant term is the number hanging off by itself, and that's just 3. All right, how about this one? G of x is the cube root of x. Is it a polynomial? If so, what is its degree? Write it in standard form, identify the leading coefficient, the leading term, and the constant term. If it's not a polynomial, explain why. This is not a polynomial, so the cube root of x can be rewritten as x to the 1/3 power. Okay? And this power is not a positive whole number, or what the book calls a non-negative integer, same thing. And since I'm using to a fractional power, this is not a polynomial. Okay, it's still a function, it's just not going to be called a polynomial. Okay, how about this one here? X cubed minus 2 over x to the 4th plus 1. Again, is it a polynomial, etc., etc.? It's not a polynomial. Okay, remember, I don't have division by x's in polynomials. I only have x raised to powers multiplied by numbers and adding those things up. And in this case, I have a quotient involving an x. So this is not a polynomial. However, it does point out the numerator x cubed minus 2, this is a polynomial. X to the 4th plus 1, that's a polynomial. But the ratio is not called a polynomial. G of x equals 9. Again, is it a polynomial? If so, identify the leading term, etc. And if not, explain why not. It is a polynomial. This is a little confusing at first because it looks like I don't have positive whole number powers of x, but I do have a constant term. And what I don't have is anything that makes me not call it a polynomial. Okay, so constants, just numbers by themselves, are considered polynomials. They're called of degree 0 because remember, we can write this as 9x to the 0 since x to the 0 is going to be 1. So we can call this degree 0. It's already in standard form because there's only one term, so I can't really rearrange it anyway. The leading term and the constant term are both the same thing because there's only one term here. So it's simultaneously the biggest and smallest power of x. Okay, how about this one? Is it a polynomial? If not, say why not. If so, etc., etc. This is actually a polynomial. Now, a lot of people will look at this and they'll say, hey, I've got x's multiplying other x's. That's bad. But this is okay because if you expand everything out, you actually end up with just a bunch of positive whole number powers of x. Okay, and the leading term is -x to the 5th. It's of degree 5. The leading coefficient is -1. The constant term is a 0. The constant term always refers to the term that's just a number with no x's, and if it doesn't look like it's there, it's just 0. Okay. So here are a couple of properties of polynomials of certain degrees because we've already studied them. So if you are of degree 0, that just means you're a constant. That is a horizontal line with a y-intercept of whatever that constant is. Okay. This book says if you are a constant of always equal to 0, they say that doesn't have a degree. A lot of places, myself included, would say that is a polynomial of degree 0. It's still a constant function. It's just the special one that happens to be the x-axis. This is not a big distinction of terminology. More important is that degree 1 and 2 we've already studied. So a degree 1 polynomial has a constant term and an x term, and that's it, x to the first. Okay, and that is a linear function. And we've studied those. What about a degree 2 polynomial? It's got a constant term, an x to the first, and an x squared, and then it doesn't have anything else, and that's a quadratic function, and we studied those in the previous chapter. Okay, so we've already studied some polynomials of degree 0, 1, and 2, and then all we do now is we say, okay, what about higher degrees? Okay. So what are some more properties of polynomials? They have this property called being continuous and smooth. This is a more advanced definition, but all continuous really means is that if you draw it, it doesn't have like jumps like this. It doesn't have holes. Okay, the domain is all real numbers, so there are no gaps in the graph. It's continuous means it doesn't have any of these jumps. It's smooth means it doesn't have sharp corners or what are called cusps, which kind of look like other corners. It just means if you draw it, it's going to do nice up and downy stuff with no, this should have been smoothed out a little bit, no sharp corners, no random jumps, no gaps, etc. Okay. So a couple, we'll just study this one extra definition in here, and then I'll make a new video fairly soon. So if you have just x to the n times a number, this is a polynomial. It's of degree n, but it only has the leading term. This is called a power function or a monomial. Just in terms of word roots, poly meaning several or many, and mono meaning one. So if it just has one term, it's a monomial. If it has many things and you're adding them up, you call it a polynomial. Okay. So a power function of degree n is just a monomial that is a polynomial of degree n. We specify that a shouldn't be equal to 0. If I was multiplying by 0, then I'd really just have 0, and the x to the n didn't belong there. So a couple properties of power functions. We'll make our way through these properties. So suppose n is an even integer. Then the function is an even function. Remember, that means that f of negative x is equal to f of x, and it means that you have symmetry across the y-axis. The domain is all real numbers. The range is non-negative real numbers, because we are raising numbers to an even power. So even if I put a positive number to an even power, I get out positive. But if I take a negative number to an even power, I also get out a positive number. So I'm not going to get negative numbers out of these even powers. Okay. There are a couple of nice points that you can always plot down. This is not a x to the even. This is just specifically without any multiplier there, just multiplying by 1, x to an even number. You always have the points 0, 0, 1, 1, and negative 1, 1. What's 0 to an even power? It's 0. What's 1 to an even power? It's 1. And what's negative 1 to an even power? It's also 1. So there are always a couple points you can draw on here. What if you had a, sorry, we're still doing even integers. Okay. If you start increasing n, the graph gets steeper in a way, but in two different ways. It gets more vertical as you get less than -1 or bigger than 1, but it gets more flat as you get closer to 0. However, as x goes off in either direction, x is going down the axis to the left or going down the axis to the right, x is getting bigger one way or the other. The function is also getting bigger, but specifically it's positive. Okay, but what if there's a positive odd integer? Okay, now I have an odd function, and remember that means f of negative x is negative f of x. That is symmetry across the origin. The domain is still all real numbers, but now so is the range. Remember, for an even power, the range didn't have any negative numbers. I never got negative numbers out. But for an odd power, you do. You get positives and negatives. Okay. And this is a typo. just to fix this. It doesn't contain the point -1, 1. It contains the point -1, -1. 0, 0, and 1, 1, these are correct. So because we're raising to an odd power now, if you take a negative number and raise it to an odd power, you do get out something negative. Some further properties when you have a positive odd integer. Very similar as the exponent increases, so x to the 3rd versus x to the 11th versus x to the 907th. These are increasing odd numbers. You are steeper when you put in numbers bigger than 1 or less than -1, but you are flatter as you put in numbers closer to 0. And remember, for even powers, as x got bigger in either direction, the function went to infinity. Here it goes to plus or minus infinity. And again, this just has to do with the fact that we're raising to an odd power. So if I plug in a very large negative and I raise this to an even power, compared to plugging in a large negative number and raising it to an odd power, well, taking a big number and raising it to a big power makes a very large number. But if I'm raising it to an even power, I'm going to get out positive. And if I raise it to an odd power, I'm going to get out negative. So that we see in this line right here, that as x goes to be bigger and bigger negative numbers, the output is bigger and bigger negative numbers because I'm raising it to an odd power. Okay, so in the next video, we'll come back and we'll learn how to graph some of these things.